easy go.
Hello friends, welcome to my channel Tech India. Today we will discuss about DC motors and how it actually works. Let's start the topic with a little experiment so that you guys understand the principle behind all DC motor that we have seen.
For this I have set up a little experiment. It consists only of a compass, two solenoids with iron cores and a switch that I will hold in my hand. Now watch what happens with the compass needle. As you have seen, I was capable of getting the compass needle into a rotary movement. You may believe me at this point or not, but what I have just shown you is a rudimentary brushless DC motor. So what exactly is going on here? Here you see a drawing that I made of the setup. The compass needle is nothing else but just a magnetized piece of metal. In other words, a permanent magnet. This permanent magnet generates a magnetic field with magnetic flux lines, which will pass the space around the needle in this way. The direction of the magnetic flux generated by the solenoid will point roughly in this direction. Now, the two magnetic fields will try to align with one another. Therefore, a force F, or actually a torque M, is applied to the magnetic needle of the compass. The needle will keep moving until the fields have aligned. Now I activate the switch again, turning the other electromagnet on, which results in a reversion of the stationary magnetic field, which we will call the stator field from now on. This will again force the magnetic needle to move, trying to realign its own field, which we will call rotor field, with the stator field. And the magnetic needle will keep on going in the same direction, because it has a mass and thus a moment of inertia, meaning that it already has a momentum towards one direction. It will keep that direction when the switching action is timed correctly. If you would now replace the manual switch by switching transistors and activate them with a Hall effect sensor rather than with my hand, you would have a true brushless DC motor. Now, of course, a brushless DC motor is built up a bit differently in real life, but as you will see, the principle is identical. From this experiment and our former lessons, I want you to keep the following in mind. Lesson 1. The underlying principle of electric motors is the phenomenon that two magnetic fields which exist inside the same space try to align with each other. When one of the fields is stationary, meaning fixed in space, while the other one is free to move, a kinetic force is applied to the magnetized piece of matter that generates the free field. That force is trying to align the two magnetic fields. A popular application, the compass. Lesson 2. In the case of electric motors, it doesn't matter if the rotor is permanently magnetized or magnetized by current flowing through a winding. It is, however, always necessary that at least one of the two elements, rotor or stator, is magnetized by an electromagnet, because otherwise you wouldn't have the possibility to reverse the direction of one of the fields periodically. Therefore, the following permutations are possible. The rotor can be magnetized by an electromagnet, while the stator is also magnetized by an electromagnet. Applications are the induction motor and the universal motor. The small-scale DC motors, which we saw before in the video, fulfill the conditions of line 2, where the rotor is magnetized by an electromagnet, while the stator is magnetized by permanent magnets. In line 3, the rotor is a permanent magnet, while the stator is an electromagnet. This is true in the BLDC, or most of them at least, and with stepper motors. The permutation in line 4 cannot be utilized to build a motor, and I don't care what any of the free energy idiots is telling me. It is not possible. Okay, for the stuff that follows now, I also want you to remember these facts. Earth's magnetic north pole is actually a magnetic south pole. That means that the tip of a compass is attracted by magnetic south poles. Second, a magnetic north pole is the location where magnetic flux lines exit a magnet while a south pole is there where the flux lines enter the magnet. Third, the magnetic field lines are always closed loops. And fourth, the magnetic flux prefers the path of lowest magnetic reluctance. Now, with this knowledge, we can tear down a DC motor and a BLDC, look what's inside, and analyze what we find. What you see here are the motor brushes. This is the commutator, and this is the rotor, which has 3 poles. And with the DC motor, it is called armature. The dark ring that you see here is the stator, which is actually a ring-shaped permanent magnet. Now, you might have seen 2-pole DC motors in school, but actually all real-life DC motors have at least 3 poles, as you will see when you tear down some of your own. The next thing that I do now is to pull out the stator magnet out of the motor's casing and try to determine how this ring-shaped magnet is actually magnetized. I do this with the help of a compass needle. Here we have a north pole . And here we have a south pole. We label the 2 poles with little stickers so that we know where they are. With this knowledge, we can now try to determine how this brushed DC motor actually works. Since the stator has only 1 north pole and 1 south pole, the field generated by the permanent magnet would look like this. You have also to consider that what we measured as north and south poles outside the ring are actually a south pole and a north pole inside the ring. So you already see why I'm urging you not to think in terms of attracting and repelling poles as they taught you in school, but to think in terms of magnetic fields that want to align with each other. When the rotor is introduced into the stator field, new, lower reluctance paths are provided so that the biggest portion of the flux will bend and wander through the rotor rather than through the air, which has much lower magnetic permeability than the silicon steel of the rotor. When now a current starts to flow via the commutator into the windings, a second magnetic field is building up around the rotor. Since the 3 coils of this motor are connected in a triangle, current will flow through all 3 windings. But because the current through that winding, which is momentarily connected directly to the source, a higher current is flowing than through the other windings, which are effectively connected in series. Therefore, the magnetic flux of that winding will overpower the other fluxes, and the rotor will shape either 1 north and 2 south poles, or 1 south and 2 north poles. As with the example with the compass needle we saw before, the stator field and the rotor field will now try to realign, applying a torque on the rotor. Once the motor is realigned, the rotor field will change its direction via the switching action of the commutator. And this will go on so that the motor keeps spinning. But enough of this, since we actually want to look at BLDCs here and not at normal brushed DC motors. For that, I show you how you can easily take a look at a BLDC yourself. You simply take an old PC fan like this one. You first remove the label, and then, at least with cheap ones like this, you also have to remove a little plastic ring from the rotor shaft. Now you can simply pull off the rotor from the stator. Next, I removed the wings from the rotor to determine its magnetization, just as I did it with the brushed DC motor before. As you can see, the result this time is that the ring-shaped permanent magnet has not 2, but 4 poles. That means that the magnetic field lines have to travel roughly in this way. This specific type is a 2-phase BLDC, and it is the type commonly used in PC fans. It has, as you can see, 4 poles, but each limb of the magnetic core actually carries not 1 but 2 windings. The 2 windings are, as in this picture, wound with a reversed winding sense, so that the current through them will generate magnetic fields of opposing direction. In many real BLDCs, the two windings have the same winding sense, but then the windings are connected in such a way that the current flow through them will be opposed, which has the same outcome. The two windings are then connected together at one end and attached to the plus pole of a voltage source, while they are connected to ground via two electronic switches. First, one switch is closed so that current flows through the first winding, generating a stator field that is opposed in direction with respect to the rotor field. Now the two fields try to align and the rotor starts spinning. Once the fields are nearly aligned, the first switch is opened and the second switch closed, forcing current through the second winding, reversing the stator field so that the rotor will spin on to align with the stator field. The stator field is then periodically reversed, and the switching action is timed by a Hall effect sensor that can detect a magnetic pole passing by. So, this is basically the principle behind brushless DC motors.
If you like my video, click on thumbs up button. If you don't like, click on dislike. If you have not yet subscribed my channel, please subscribe to get latest updates. So friends, goodbye and see you soon in our next video.